Hi, this is our harmful algae bloom forecasting project. So, a bit of a table of contents. We will first go over the background behind our project, like what is an algae bloom, the motivation, why we our approach to this project, and the reasoning behind it, the data set we use for our project, and the method what we actually did for the project, and the results, our actual findings for the project. So, a bit of an introduction to the project background. So, what is an algae bloom? Well, algae blooms are basically rapid growths in algae in the coastal waters, and then they can actually discolor water, reduce oxygen, and release toxins. For example, in our offshores of California, these algae periodically bloom completely out of control. Now, predicting these 1 week in advance is very important because it helps public officials to respond to these health concerns caused by the algae, and it also tells coastal facilities to shut down the equipments before they are damaged by the algae. And then in Southern California, the most common is this thing called Lingodimium polydrium, and this algae. In fact, half the samples we have in scripts are these lingodimiums. And what's really unique about these is that when you disturb, they release a bioluminescent light. And that's the goal of our project. In this project, we wanted to create a model that basically, given the features of the water, can predict whenever the waters will release this bioluminescent light. Now, the motivation behind our projects and what makes this problem really challenging is that these blooms are, first of all, driven by many interacting factors. For example, the nutrients in the water, the wind, the plankton communities, and also these systems tends to be very non-linear and chaotic. So a small change in one feature can have huge effects in the bioluminescence in the linguodimium. And because of this, traditional statistical models are very bad at just capturing this complexity because it's just so non-linear and so chaotic. Another issue is that our data set tends to be very noisy and limited, especially for species specific events like neodymium, because these data collections really depend on the device that we are used, and because of this, the data sometimes vary and are not always point perfect. And because of this, like these deep learning models, big deep learning models, also kind of don't understand these values that well, just because the data set itself is just so noisy and it might lead to a really bad prediction. So our motivation for this project is that what if we utilizes the mechanic understanding of these traditional models, combine it with deep learning models for the predictive modeling, and combine the strength of each to see how the results are going to be. And so a big introduction to the data set. The data set, we're very lucky to have the data set provided by Professor Lisa Carter from the Scripps Institute of Oceanography. The data set actually spans 16 and a half years, and they are collected weekly with a total of 823 observations. And here are some of the features that are included in our data set. Now, the actual methods, what we did for the project. So how we approached this project is we approached it in four main steps. First of all, we used CCMs to just identify what features actually affect linguodinium, to look at each features in our data set and filter out the features that just don't really affect linguodinium at all, and then focus on the features that do. And after we figure that out, we run it through an EDM, empirical dynamic modeling. So these help us capture these nonlinear ecological dynamics from the time series data. And then we basically start using building a lot of these EDM models to build multiple ensembles, multiple EDM predictions of local models to represent the system behavior. And once we have these stack of EDM predictions or EDM embeddings, we then run it first to a trust gate because some EDM embeddings just aren't that good. They're kind of random and some are. So we first run into a trust gate to filter them out and a attention gate to grab the features that are actually important. And once that is all done, we feed that to an LSTM to predict, to see, given these well performed EDM embeddings, to see how the EDM can use it to predict future blooms. And then from our result, we can see that our approach of using this hybrid EDM LSTM really outperformed just feeding the LSTM raw data. As you can see here, if we feed the LSTM raw data, the AUC barely surpasses 0 0.6. However, if we use the hybrid approach, we see an almost 12% increase. And this is consistent after multiple runs. And here we run it 60 times, and you can see it goes better in in most metrics, in both test AUC and validation AUC.